Suppose that you have a square in which the length of each side is called x. We know that the area of the square will be x times x, or simply x squared. This is the most basic form of a quadratic, and we can see here other examples of quadratics. Notice that there is something that all these have in common, being the x squared term. And that's the exact definition of a quadratic. We can define a quadratic as a polynomial with a degree of 2. There are three different ways to write a quadratic: standard, factored, and vertex form. In this video, we will focus on writing from standard to factored and from factored to standard form. We have the equation x squared minus 16 equals 0, and we want to rewrite it in factored form, in which we have two solutions to this equation, p and q. In order to find these two solutions, we want to start off by rewriting the equation into x squared equals 16. We know we can do this because we simply added 16 on both sides. From here, we take the positive and negative square root of both sides, and we're left with two solutions, x equals 4 and x equals negative 4. We know that 4 works because if we substitute it into this original equation, we get 4 quantity squared, simply means 4 times 4, and we know this is 16. So 16 minus 16 equals 0. So this is good. And we also know that negative 4 quantity squared equals negative 4 times negative 4. And as we were multiplying two negatives, we get a positive 16. And we know that we can substitute in 16 here, and 16 minus 16 equals 0. So this also works. Now, since we have two solutions that work, we know that this is our p and this is our q. So we can rewrite this expression as x minus 4 and then x plus 4. Notice how these two expressions, so let me take this expression here, and looks like we missed an x, so let me rewrite that x. X squared minus 16 equals 0. If we plug in 4 into this equation, we get 16 minus 16 equals 0. So it equates to 0. This is our goal. So if we plug in 4 into this equation, this portion evaluates to 0. And we know that 0 times anything equals 0. So we know that 4 also works for this equation. And if we plug in negative 4, this portion evaluates to 0, meaning that 0 times anything equals 0. And this shows that we can rewrite any quadratic in standard form into factored form, which is right here. So as such, we have successfully rewritten this equation in standard form into factored form. So we have two quadratics here in standard form, and we want to rewrite both of these in factored form. So we can start off with the first equation by adding 64 on both sides. And like we did on the other problem, we take the positive and negative square root of both sides, and we're left with two solutions, x equals 8 and x equals negative 8. Using the factored form right here, we can rewrite it as x minus 8 and x plus 8. And so we know that if we substitute this state right here, we would get 0, and 0 times anything equals 0. And likewise, if we take this negative 8, we know that negative 8 plus 8 equals 0, and 0 times anything also equals 0. So we have rewritten this equation into factored form. Good. Now we have this equation right here, x squared minus 25 equals 0. So we do the same process. Add 25 on both sides, take the positive and negative square root, positive and negative square root, and we're left with two solutions, x equals 5, x equals negative 5. And using our factored form, we have x minus 5 and x plus 5. And once again, if we substitute 5 here, this evaluates to 0. So this entire thing equals 0. And if we substitute in negative 5 here, negative 5 plus 5 equals 0. So 0 times anything equals 0. Now, if we take any quadratic in general, written in the form x squared minus a squared, so a number a that is squared, this is simply equal to x plus a and x minus a. So just because you see this negative a squared here doesn't mean you should get scared, because we see it right here. This is simply 5 squared. And then we see it also right here, which is simply 8 squared. So we know that if we have this 5 right here, so this 5 squared, we can rewrite it as x minus 5 and x plus 5. And also if we have this negative 64 right here, which is simply 8 squared, we can write it as 8 and 8, right? So in general, this is called difference of squares. And this is simply a trick that you can apply to quickly solve a quadratic written in this form. In general, with the difference of squares property, we can take this a term right here and split it off into a positive part and a negative part. So for instance, x squared minus 25, we know that this is simply 5 squared. So we can take 5 and split it off into a positive and a negative part. So let's quickly see why this works. We take the square in which we started the video off with, except this time our left side is going to be x plus 5 and our top side is going to be x minus 5. So in order to find the area of the entire square, we take the area of each individual square and add it up to get the total. So let's go ahead and do that. We know at the first square we have a length of x and then x, so this is simply going to be x squared. And the second squared right here, we know that we have a side x and then we have negative 5. So negative 5 times x is negative 5x. In this third square right here, we have a positive 5 and an x. So this reduces to 5x. And finally, in this last square, we have 5 times negative 5. We know this is negative 25. And so in order to have the total area of this square, we will add each individual square. So we take each individual square and add it up to find the total area. You will notice that these two terms cancel out into 0, and so we are left with our original expression, x squared minus 25. In this quick visual proof, we saw why difference of squares works, in that we took x plus 5 and x minus 5, which is simply x squared minus 25, and made it into a square, in which one side length is x plus 5 and the other one is x minus 5. And in order to get the total area, or in other words, the original expression, we would have to calculate the area of each individual square and add them all up at the end to obtain the original expression. So far you've noticed that we've taken standard quadratics in the form of y equals ax squared plus c. So for instance, the a term here is equal to 1, so it's still ax squared plus c. Now, what we're mostly missing is the bx term, except that in difference of squares, all that happens is that the b term cancels out. And so we will quickly find different strategies to factor quadratics with the b term, and will differ a little bit from difference of squares. We have a quadratic written in the standard form y equals ax squared plus bx plus c. And this time you may notice that there is a middle term, which we call b. In our previous quadratics, we've simply subtracted the non-x squared terms from both sides, so both of these do not have an x squared, and then we've taken the positive and negative square root in hopes that we get two solutions. But this time you may notice that this strategy doesn't work, because we know that this really doesn't tell us anything about the solutions to this expression. So we actually have devised a new plan to hopefully find our two solutions to this quadratic. We want two numbers which we will again call P and Q that add up to B. So P plus Q should equal B, and that multiply to C. So P times Q equals C. In this case, we know that B equals 4. B is our middle term. It is 4. And that C equals 3. C is our last term, and it is 3 in this case. So what two numbers could work? P could equal 1, and Q could equal 3. Why is this? We know that 1 plus 3 equals 4. So P plus Q added to B, so then B equals 4. So this works. And we know that 1 times 3 equals 3. And this is also what we wanted, because if we take these two numbers, they multiply to C. So this also works. Now that we have these two numbers, we can rewrite it in the factored form, x plus 1, and then we would have x plus 3. And this entire thing should equal 0. And now we want a number, we want two numbers actually, that when added, or two distinct numbers, that when we substitute it here, should give a 0, and that when substituted here, should give a 0. So these two numbers, so in other words, x plus 1, 0, and then x plus 3 should equal 0, because we know that if one of these equals 0, then the entire expression would equal 0. So let's solve these two. We get x equals -1, because -1 plus 1 equals 0, and then x equals -3, because -3 plus 3 equals 0. To recap, we found two numbers, P and Q, that add up to B, so P and Q equals B, and that multiply to C, so P times Q equals C. And using these two formulas, we know that x squared plus 4x plus 3 simply equals x plus 3 times x plus 1. And to verify that, we will once again use our useful square, in which one side is x plus 3, and the other side is x plus 1. And recall that we want to find the area of this entire square, and to do so, we will compute the area of each individual square and add it all up at the end. So let's go ahead and do that. We know that the area of the first square is still x squared. We know that the area of the second square is x times 1, which is x. We know that the area of the third square is 3 times x, so 3x. And lastly, we have 3 plus 1, or 3 times 1, which equals 3. So the total area of the square will be x squared plus 3x plus x plus 3. And notice how we returned to the original expression, which we wrote right over here. Notice how in the difference of squares example, these two terms canceled out. But this time they will not cancel out, meaning that we have a b term that results. We now have a different quadratic expression, x squared plus 6x plus 8 equals 0. In order to factor it, or in other words find its solutions, we want two numbers, p and q, such that p and q add up to b, and p times q multiplies to c. We know that b equals 6, as it is our middle term right here, and that c equals 8, as it is our constant term here. So two numbers that add up to 6 and two numbers that multiply to 8. We know that these two numbers could be 4 and 2, because we know that 4 plus 2 equals 6, which is our b term, and we know that 4 times 2 equals 8, which is our c term. So we can go ahead and rewrite this expression as x plus 4 and x plus 2. We're looking at these two numbers equals 0. And again, to find the solutions, we simply set both of these equations equal to 0. Both of these equal to 0. And we're left with x equals -4 and x equals -2. We have the quadratic expression x squared plus 8x plus 16 equals 0, and we want to find two numbers, p and q, such that p and q add up to our middle term, b, in this case 8, so p plus q equals 8, and multiply to our c term. Our c term is 16, so p plus q equals 8 and p times q equals 16. So these two numbers are 4 and 4, because we know that 4 plus 4 equals 8, and 4 times 4 equals 16. So we can go ahead and rewrite it in factored form, and we would have x plus 4 times x plus 4 equals 0. And we have two of the same terms together, so we know that we can rewrite this as x plus 4 quantity squared, same two terms, equals 0. And from here, we realize that our only solution to x is -4. Why? If we take x plus 4 quantity squared and take the square root of both sides, we know that the square root of 0 is simply 0, and that the square root cancels out. So x plus 4 equals 0. Therefore, x equals -4. In this case, we only have one solution, and we will see why. So using our square method again, we can take the original expression and convert it into factored form, and once we have these two, we can set it to the length of a square and compute the total area, which should give us the original expression. Now notice how these two lengths are the exact same. They're both an unknown number plus 4, meaning that they are the same length. Same length. And in general, when you have two of the same factors, or simply the quantity squared factor, you call this a perfect square. So a perfect square is what you would call this. So this original expression is a perfect square. This expression is a perfect square, and this expression is a perfect square, since they're all equivalent. And the reason we call it a perfect square is because both of the side lengths of the square are the same. And since we know that in a square, both of the side lengths are the same, we would call it a perfect one. So again, just to check, this square is equal to x squared, this one to 4x, this one to 4x, and this one to 16, meaning that our total area is x squared plus 8x plus 16. So remember, if you can write a quadratic in the form x plus z, we'll call our number z, quantity squared equals 0, then you will have a perfect square. Just to get a little bit more practice here, we have the quadratic equation x squared minus 5x minus 6 equals 0. And we want two numbers, p and q, such that when added, it should equal our b term. Our b term is -5. So this is our b term, and we write -5. And that its product, so when multiplied together, should equal the c term. So -6 is our c term. So what two numbers would work in this occasion? Well, we know that p could equal -6, and that q could equal 1. Why is this? We know that -6 plus 1, so when added, equals -5, and that when multiplied, it gives us -6. So these two p and q should work. Now let's rewrite it in its factored form. So x minus 6, or p, then x plus 1, or q. And again, to solve for the zeros in this equation, we would simply set both of the factors equal to 0, meaning that x equals 6 and x equals -1. So these would be our solutions. So here's another example. X squared minus 20x plus 51 equals 0. So p plus q, our two numbers, should add up to negative 20, which is our b term. P times q should multiply to 51, which is our c term. So what two numbers add up to negative 20 and multiply to 51? These two numbers would be negative 17 and negative 3. Negative 17 plus negative 3 equals negative 20. Likewise, negative 17 times negative 3 equals 51. So we can go ahead and rewrite this as such into our factored form, meaning that x should equal 17 and that x should equal 3. We have the quadratic equation x squared minus 16x plus 50 equals 2. Remember that we want it to equal 0, so what we're going to do is subtract 2 from both sides, meaning that we're going to get x squared minus 16x plus 48 equals 0. And now, since it's equal to 0, we can go back to our method and find two numbers, p and q, such that p and q add up to b, so b is negative 16, and that p times q should multiply to 48. So now what two numbers add up to negative 16, negative 16, and multiplies to 48? In this case, we will see that negative 12 and negative 4 satisfy these two equations here. So let's go ahead and rewrite it. X minus 12 times x minus 4. And this means that our two solutions are x equals 12 and x equals 4.